So chapter number 5, chemical formulae, equations and calculations, part 1. Okay, what we do is that we start with chemical equations, their types, and how to write them as the first thing in this chapter. So as soon as we come to chemical equation, the chemical equation actually has many types, but we first bifurcate into just two, and that is word equation, the equation that is written in the form of words, and symbol equations, the equations in which we use the symbols right out of the periodic table. Word equations are pretty easy, actually. You write the names. If you know the names, that's easy. And don't worry, we are going to tell you how to name the compounds in later chapters right after bonding so that you would know how to come up with their names. And of course, the symbol equations are a little bit difficult because they are supposed to be balanced. Actually, all equations are supposed to be balanced, but the words are good enough to balance equations. The symbol equations become a little difficult. For example, take a look at this equation. This is a balanced chemical equation. We call it a balanced chemical equation because apart from formulae that you can see over here, you would notice there is a number 2 right beside or before HCl. These are known as coefficients. These are sometimes also known as molar numbers. This 2 is actually being multiplied with all the atoms written after it in this compound. All right. So the numbers written at the bottom are usually the number of a specific atom, but the numbers written as coefficients, which means the entire molecule or the entire substance. Okay. So I hope you already understand that how we balance these numbers. If there are two numbers, the one written on the left, let's say we have this number and we have this number. That means how many atoms of calcium are there?
Wait, no, for calcium only 6.
And how many chlorine atoms are there?
6.
6. So you already know you need to multiply these numbers as there is nothing written below calcium. So it has one atom originally in this compound, but in the case of whole thing, it becomes 3. I'm using the word atom doesn't necessarily means they are present in the form of atoms. However, as soon as we go ahead to the bonding chapter, I'll clear it out what that means because calcium is actually present in the form of ions in this case. Now, there is another balanced equation in which H2 is 2O7, which is actually oleum, is reacting with water. It's producing sulfuric acid, H2 is a 4. And you can see the numbers we have written before sulfuric acid. This means there are 2 of these compounds present. This diagram is drawn in such a way, give you an idea that how we work with it. Now, in case of balancing of equations, we need to work in such a way that you can get to this numbering correctly. Now, for example, this is methane. The structure is drawn like this. The formula is this, and this is oxygen. This is carbon dioxide, and this is finally water. When I write these structures, you would easily notice that carbon is actually shown with big black balls, oxygen red color, and finally hydrogen as white, which you can see through the entire equation. Now, this is pretty easy to see, but actually what comes in front of you in papers is something like this. Now, before I move on, I'm going to just give you 3 simple set of rules to balance the equations correctly, quickly, and efficiently, right? Most of the times these rules are not written in the books, but I am going to give you these rules in terms of preference to give you an idea how to balance it. Students do know how to balance it, and even that too correctly, but the part that they don't know is to how to do it correctly and quickly. Fastest and flawless is something that you should be good at when it comes to balancing of equations. Now, first rule, try balancing all other elements first and keep oxygen or hydrogen for the end. All right, balance them in the last if possible. Maybe there are some equations which do not consist of hydrogen or oxygen at all, fine. There are some equations which are completely made up of hydrogen and oxygen, understandable. Those equations might be the case, but for the rest of them, like this equation, you would see three elements, carbon, hydrogen, and oxygen. Start with carbon first. Although this rule is first one, but the second rule has a stronger preference than rule one. The second rule is if there is a species, an element that is present in one compound on left-hand side, and it's actually distributed in multiple compounds on right-hand side, always keep that element for last. If I look at these two rules together, that tells me first I have to balance carbon. Secondly, I have to balance hydrogen. I'm keeping oxygen for last because oxygen is present in just one species on the left, but is distributed in two different species on the right. Remember, this element is for hardest for you to balance at start. If you keep it for the end, it might come easier to you. If you've already balanced a few elements before them, the element that has been bifurcated into different species is easiest to balance at the end. So keep it for the end. All right. Now, what I'm going to do is that we keep this list in mind and we are going to balance the entire thing. Let's try it. So starting with carbon, there is one carbon over here and one carbon over here. It means we do not need to balance carbon first. Starting with hydrogen, there are four hydrogen over here, but two over here. Of course, I need to write two over here in order to make them four. As soon as I do that, I actually disturb the entire oxygen balance, which means sometimes you need to go through the list again. If I might have disturbed carbon, I would reinitiate with carbon again. So that's what makes balancing of equations a little tactical. All right. So as I've balanced oxygen, doesn't matter. I still need to balance. I needed to balance oxygen in the first place. So let's get started with it. There are two oxygen atoms over here. There are two over here, and two into this. 2 plus 2 means 4. So I simply write 2 over here to make them 4, and there you go. I've balanced the whole equation. Get the point?
Yeah.
Okay. Are you good at balancing equations?
I'm okay.
Okay. So let's try a few equations in order to get that right. Now, what I ask my students is that these methods, the one written over here in terms of numbers, number of atoms, the one given over here in terms of diagrams, the 3D diagrams, these are childish methods. You can begin with these methods. They're very good baby steps, but remember, these are just baby steps. What I ask my students is to balance the equation. As soon as you're done with these baby steps, try writing the equation in such a way that you keep some space on the left of every substance or species, like this, so that you can write numbers and cut numbers or overwrite them again and again in order to balance them. Okay. Now, zinc, zinc, chlorine 2, chlorine 2. So I'm going to write 2 over here, and hydrogen is automatically balanced. I hope you get the point. If you need to change a number, let's suppose this 2 is wrong, you need to balance it again. Cut this 2 with a single line cut, write 3. Cut this one, single line 4. You can increase the numbers in this way. So you can balance the equations with numbers right over here. All right. Do you know
Yeah.
how to annotate on the screen?
Yeah.
Okay. The annotations are already on. Why don't you try balancing this equation for me? Sodium, when reacts with oxygen, produces an oxide, which we call sodium oxide, the formula for which is Na2O. Why don't you go ahead and balance this whole equation for me?
Okay.
Use a different color than red, please. All
Done.
right, good, good, very good. Now, I insist you to do one thing next time you go. If you were thinking to put 2 over here, write this 2 first before you go for a single line cut over here and writing 4 over here.
Yeah.
This was a simple equation. This only consisted of 2 numbers. The equations, the bigger ones that may consist 4 different numbers at 4 different positions in the equation, whether with reactants or products, you are going to get confused if you keep the numbers in mind and don't write them on paper. Try not to keep the numbers in mind. Try writing them
Okay.
before you start changing the other numbers. This is a very good hint in order to not get the equation incorrect. All right. Before I move on, this hint is pretty important. You can never change a formula. All you can do is that you can write numbers to the left of every substance, and that's about it. Changing a formula means you can never make changes to the subscripts. You cannot make changes over here, over here, over here, or write anything in between. All right?
Yeah.
This would actually disturb the whole thing. Now there comes an equation I like. Okay, but it's unfortunately balanced over here. So let's not try it on this page. Try the same equation on this page. C2H6 plus O2. This is ethane. This is the gas commonly used for burning purposes. As a fuel, it produces carbon dioxide and water, just like methane we commonly use as a fuel. Go ahead, balance it up. Good.
We can write fraction numbers, right? To for balancing.
The only fractional number allowed for you to write in exams is 0.5. You can't write 0.4, 0.3, 0.2, 0.1, 0.7, 0.8. You can
Yeah.
only write whole numbers and halves. By half, I mean 0.5. Good. So either you could have wrote 0.5 along with it, right? Or the
Yeah.
other option you can do is that you can multiply the whole equation with 2, which makes this one as 2, this one as 7, this one as 4, this one as 6. Either you write it this way or you write it like this. Both of them are correct. All right. Sometimes they tend to write the equation and give you the blanked areas, the lines, the blanks to fill it up, like something like this. A blank over here, a blank over here, a blank over here. If they give you 3 blanks, that means you need to write the decimal and this is 1. If they give you 4 blanks, you can fill it up either in this way or in this way. It's completely optional. But if they don't give you a blank over here, that means you need to fill it up with a decimal number. Get the point?
Yeah.
The blanks are put there sometimes to confuse you. Well, I haven't seen blanks in past 5-year papers of Edexcel, but if we go way back like 2013 or 12, I saw a paper there with blanks, right? That's why I'm telling you this, because they have given it in past, they might give it again. Okay, the same thing is given over here, as well as the whole equation. It's entirely up to you. Okay, let's go for a difficult equation. Let's write something that might take a little bit of time for you to balance. Okay, and
Okay.
I am going to leave a lot of space for you by writing it in this way. If I write it straight, it would take much more area. So it's better if I write it like this. NH3 is ammonia. Go ahead, balance it up. So
Okay.
NH3 is actually ammonia. Ammonia, when reacts with oxygen, produces an oxide of nitrogen, nitrogen oxide, as you can see in front of yourself. It also produces water. This equation will use numbers starting from 4 or above. It won't use 2, it won't use 3. These are very small numbers for this equation. So when you work on this equation, you might need to write 2 or 3 first, but as soon as you move forward, you would see that it is filled up with bigger numbers. However, if you use decimals, you may finish an equation with some smaller numbers. The 4 and or above I'm talking about is just for the whole numbers. You can start working on the equation at the same time. Listen to me.
Okay.
All right?
Yeah.
Okay, good. Go ahead. Right. Good. So far, so good.
Oh, yeah. Done.
All right, good. Well done. Um, Actually, that's not correct. You still don't
Oh.
have balanced oxygen.
Oh, yeah.
These two chapters,
Okay, so yeah.
go ahead.
I was just thinking, so would this be 2.5?
2.5. Now you're right. So these two
Yeah.
chapters are going to take a lot of practice. They consume time because of practice. This formula equations and the whole thing, part 1 and part 2. Forgot the name of the chapter. All right.
Yeah.
So 2.5. If we hold this up, this would become 4, this would become 5, this would become 4, and this would become 6. Sometimes I have seen students coming up with bigger numbers instead of smaller numbers. You went on with the smaller numbers. That's a very good way that you wrote it with. But sometimes I have seen students doing it like this. If you end up with bigger numbers like this, always try to check, can you simplify all the numbers in the equation in one single go with one single number? If you can, always revert to smaller numbers, because bigger numbers may seem correct, but actually you get yourself some marks cut because of that, usually a mark, right?
Yeah.
So always see if you can simplify all the numbers in the equation, not some selected numbers, all the numbers in an equation. Okay. Let me give you another tip. Sometimes, and this is a mathematical tip, this is not much of a chemistry tip. Sometimes the equations may consist of numbers and actually prime numbers at both the ends. If that happens, you can balance them in a single go. For example, if you look at it, one aluminum over here, one aluminum over here. We have two chlorine over here, three chlorine over here. If you want to go with whole numbers, sometimes students write 1.5 over here. And then you have to write 1.5 over. Then there would be many decimals along the equation. This doesn't look good as written in the key point over here. Doubling everything is a better idea, a much better idea, right? So I would suggest for prime numbers, as 2 is a prime number as well as 3. Remember, according to maths, the prime numbers are the numbers which are only divisible by either 1 or themselves. So switch the prime numbers, multiply this one by 3 and this one by 2. When you're dealing with prime numbers on both ends, it's the best way to deal with them. If you start with small numbers and go all the way to bigger numbers, it's just simply better to multiply different prime numbers. It had 3 over here, so I multiplied this by 3. It had 2 over here, so I multiplied this 2 over here. Get the point?
Yeah.
Afterwards, I can simply write a 2 over here. There you go. You balance the equation. Okay, so this is much more of a mathematical tip than it is a chemical one. Okay.
Yeah.
If you want, I can give you more equations to balance, but for now, let's move further. State symbols. State symbols are the symbols we usually write next to a species in the equations to give a good idea to the reader that which state it was in. S stands for solid, L for liquid, G for gas, AQ for aqueous solutions or dissolved in water. Remember, state symbols are always written in small letters, as we mostly use capital letters for the starting letter in the symbol. All right, so it's better to write them in brackets and in small letters. For example, this equation quickly tells us that potassium was present in solid form, water was in liquid form, the QH that was made as a product was in aqueous solution, and it also produced hydrogen as a gas. So there are all 4 states in a single equation. All right. How much of
Yeah.
each substance reacts in a chemical reaction is something that we are going to calculate in terms of formulae. All right. And
Yeah.
before I move with that, two important hints. Don't worry if the chemistry is new to you. You won't know state symbols at start, but don't worry. As soon as we're going to go through chapters, you would know the state symbols of the most common things that you're going to handle. The first 20 elements, and for most of their compounds, you would know what state symbols you need to write. Okay. And if there is something unfamiliar in exams, remember they tend to write the state symbol in form of words in the question. The metal was taken in solid state for the reaction. There you go. You know, even you metal name is new to you. You know that you are supposed to write S next to it in the chemical equation. So try looking for hints in the question apart from what you already know or you remember from the book. Next, water is a liquid and not an aqueous solution. So water can never be AQ, all right?
Yeah.
Moving on, as we are going to proceed to the calculations part, the formulae part, so we need to work closely with AR, relative atomic mass. Remember, we defined it back at chapter 3, and we already know that this is an average of all the naturally occurring isotopes of an element. Now, atoms are amazingly small, mass is so less, we don't use these masses. What we do is that we compare the average mass of an atom with carbon-12 isotope. We call this carbon-12 scale. On this scale, one atom of carbon-12 isotope exactly weighs 12 units. That's why we are using this. And the mass of most common hydrogen isotope is 1, which is a much simpler number to use. So instead of coming up with these numbers, this one or this one on the list, we come up with much simpler numbers. That's why we use relative atomic masses And that's why relative atomic masses are quoted in the periodic table and not the actual ones. Remember, isotopes are the atoms of same element which have the same proton number but different mass number. That is something we have described previously. Now, there is a slight approximation. To be accurate, each of these hydrogen atoms have a mass of 1.008 on carbon-12 scale, but we take it exactly 1 to keep IGCSE simple and easier at this level. But remember, get ready for something like this for A levels. It is going to be easy just at the level of IGCSE. In A levels, you're supposed to go with at least 2 or 3 decimal numbers ahead to it. And you're supposed to be very accurate in A levels. Now, the basic unit on the carbon-12 scale is 1/12 of the mass of carbon-12 atom, which actually becomes 1, because if you're going to divide 12 by 1/12, you know that the answer is going to be 1. So that's the basic unit. That's how we define it for relative atomic masses. Moving forward, the relative atomic mass of an element is then given as the AR symbol in the exact definition, which has been a part of past papers. So remember, you're supposed to memorize these 3 lines as a definition. And remember, in both the papers, there is at least one definition of 1 or 2 mark, at least one. They can be as many as 2 or 3 in a paper, but they at least ask one definition. So make sure you do not miss on these words. Every word of this definition is important and has its own significance in order. So the relative atomic mass of an element is weighted average of the mass of isotopes of that element. It is measured on a scale on which carbon-12 atom has an mass of exactly 12. So we explain the scale too. Remember, weighted average is the average so that we know how much each isotope is contributing. And if you remember back from chapter 3, the isotope that was more abundant in nature contributed much more than the isotope which was less abundant in nature. There may be some elements which have 0.5s in its relative atomic masses, like Cl and Cu. Okay, so
Yeah.
moving on. Relative formula mass, I think this is something that should be pretty easy for you. And so far, you might have calculated the formula masses from the periodic table as well, right? I hope you know
Yeah.
how to do that. For example, for MgCO3, we need 1 atom of magnesium, 1 of carbon, and 3 of oxygen. So that's the way we add them up, and the MR is 84. However, this becomes a little tricky if you're going with something that consists of bracket. A bracket means that we're going to multiply the number written at the bottom of the bracket as a subscript with everything inside the bracket. This bracket is pretty simple. Do you know how to solve this bracket and get this mass MR 74?
Yeah.
Okay,
We
then
times
solve this bracket for me because it's going to be a little bit trickier. Sorry, than this one. Why don't you go ahead and calculate this one?
yeah.
Let me
Okay,
help you with
so
it.
yeah.
Aluminum is actually 27, sulfur is 32, and oxygen is 16. Make sure you have a calculator nearby because in these 2 chapters, you can't work without a calculator.
Yeah.